So we are going to go ahead and talk about everyone's favorite scientist, Newton, and about his laws of motion that govern the world around us. The first law we're going to talk about is obviously Newton's first law of motion. This is also sometimes called the law of inertia. This law says an object at rest will stay at rest. An object in motion will stay in motion at that constant velocity. Now remember, velocity is both speed and direction unless acted upon by an unbalanced force. So let's talk about what this means. Here we have a soccer ball, and it's currently at rest. And it will remain at rest, not moving, until an unbalanced force, like a foot, acts upon it. When that unbalanced force of the foot kicking the ball acts on it, the ball will remain in motion in a constant speed and a constant direction. In other words, a constant velocity, unless it's acted upon by another unbalanced force, and here we see that in the net. So that is what Newton's first law of motion says. Now you might be asking yourself, well then why do everyday objects seem to slow down or become motionless without forces, right? It doesn't look like anything's acting on it. The answer is friction. When you push a box across the floor, it will slow down because of friction acting upon it. So our first law of motion, if we apply it to this golf ball, if we hit this golf ball, if there was no unbalanced forces acting on it, the golf ball would never stop. But there are unbalanced forces such as friction, even air resistance, oopsies. All of those are unbalanced forces acting on that golf ball. So I want to talk to you about this idea of inertia. Inertia is the tendency or likelihood of an object to resist change in velocity. And this applies whether an object is moving or whether an object is not moving. And inertia is different based on the object that we're talking about. And inertia is based on one thing, and that is mass. The higher your mass, the less likely you are to move. It's harder to get you to start and stop. The lower your mass, the more likely you're going to move. So let's talk about this. If I have a 4 kilogram box and a 2 kilogram box, this 4 kilogram box has a higher mass. So it is more resistant to change. It has a higher inertia. It is more resistant to change than that 2 kilogram box. So Newton's first law is super important to your life, especially as you start driving a car or when you are in a car. Because of inertia, all objects resist changes in their motion, right? When you're going 80 kilometers an hour in a car, and all of a sudden you hit a brick wall or another car or anything, your body inside of the car does not stop moving. It will continue to move at 80 kilometers per hour. And this is how people go through windshields. Because while the car has stopped, your body still has inertia and you will fly through the front windshield. Guys, this is my little PSA to say, please wear your seatbelts. Be safe. Please wear your seatbelts properly. So Newton's second law of motion, we're going to investigate that now. And Newton's second law of motion comes with a really fun equation called F equals ma. I have even rewritten that this year to be called the FAM equation. So F equals am, Remember, in multiplication, it doesn't matter which we do first, and it's easy, I think, to remember fam. It kind of spells fam, like family. So F equals ma or F equals am. This says the net force of an object is equal to the product of its mass and acceleration. So we have F equals ma, my mass equals force divided by acceleration, and acceleration equals force divided by mass. And these, these right here should all be, should be a lowercase a, and this should be a lowercase m. There we go. So as a reminder, a force is a push or a pull, and it causes the object to change its motion. So 1 Newton, this is our unit for force. You've seen it before with just as a capital N. So 1 Newton is equal to the force required to accelerate 1 kilogram of mass at 1 meter per second, or meters per second squared. So when mass is in kilograms and acceleration is in meters per second squared, the unit of force is in newtons. So let's look at some practice problems here. This is asking us to find how much force is needed to accelerate a 1,400 kilogram car 2 meters per second. Well, the first thing I always do when I solve problems is write the equation. F equals ma, or F equals am. Now I'm going to fill in my numbers. Force equals my mass, which is 1,400 kilograms. Please make sure you include your units in your equation. It's very important. My acceleration is 2 meters per second squared. And now I'm going to solve that. And I'm going to get 2,800 kilogram meters per second squared. But we just learned on the previous page that this becomes newtons. So I get 2,800 newtons as my answer. So I want us to go ahead and fill in this diagram together. Remember, we know our simple equation, which is F equals ma. So here I need to find what goes in this box. And I have that 20 newtons equals my mass, which I don't know, times my acceleration, which is meters per second squared. And so I will get my mass as 4 kilograms. So I'm going to put 4 right here. And then here, I need to solve this one as well, right here. And I need to find my net force. So my force is going to equal 1 kilogram times 10 meters per second squared. And that is going to get me 10 newtons. On your paper, I would like you to compare some of these things. Notice, what happens when I double my acceleration? Notice, what happens when I double my mass? Oops, we forgot one right here. Let's figure out this one too. So, if 10 newtons equals 5 kilograms, what is my acceleration equal? 2 meters per second squared. So I have 2 meters per second squared there. So what happens when I double my acceleration? You should see when I double my acceleration, my net force also doubles. So there's a direct relationship between acceleration and our net force. When I double my mass, and I'm also halving my acceleration, we notice that our net force stays the same here. So what does this mean? What can we conclude from this data table? What we can conclude is that if the mass remains constant, doubling the acceleration doubles the force. But if the force remains constant, doubling the force reduces the acceleration by half. So it's important to know these relationships, right? If I tell you that I have this object and it weighs X, and I have this object and it has a mass of 2x, you should know that doubling this mass will also double my force. So weight is also a force. Weight is also a force. That is a very, 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 very important statement. Weight is also a force. And because weight is a force, we can rewrite our F equals ma equation specifically to address weight. So remember, weight is the resultant from our mass being acted on by gravity. And our equation for weight equals mass times gravity. Gravity is always 9.8 meters per second squared on Earth. You definitely need to know that and have that value for gravity memorized. I would like you to try these practice problems. Go ahead and pause the video and then tune back in to see what the correct answers are. So these should have been the answers that you got. Please let me know if you have any questions or concerns, or if there is anything I can do to help. So one of the things we need to talk about is an application of Newton's law and how we can see it in our daily life. Newton's law is really important because it explains why different masses accelerate to the Earth at the same rate, but with different forces. All right? This means that if I drop a 10 kilogram object and a 1 kilogram object, they will hit the Earth at the same time. Now, there are things that prevent that from happening, right? Like air resistance. However, this is the law that tells us that in a frictionless, air-resistant free world, a 10 kilogram object and a 1 kilogram object will accelerate at the exact same speed towards Earth, although they will hit with different forces. And I'm going to ask you to check out a video that's also in this section, and it's called Newton's Second Law Application. So please go watch that video. It's really awesome, and it talks more about this problem right here. We are down to Newton's last law, his third law of motion that we're going to talk about in our class. So Newton's third law of motion says that for every action force, there is an equal and opposite reaction force. And this occurs, though, this is the caveat, between paired objects only. So what does it mean? So whenever objects A and B interact with each other, they exert forces that are equal and opposite. So here you are sitting in a chair. Your body exerts a downward force. That's the force due to gravity. And an upward force. That's our normal force. And there are equal and opposite forces that take place right here. That is what Newton's third law of motion says. So action-reaction forces are between paired forces. That's what I said in the previous slide. They do not act on the same object. Now this is a little bit of a confusing definition, so we're going to investigate a little bit more what this means. Here we have this cute little fish in his scuba gear, and he is going to swim through the water. And the way that he's able to do that is because of Newton's third law of motion. This fish is going to use his fin to push onto water. That water is then going to push back on his fin with an equal and opposite force. And this process will allow the fish to be propelled through the water. And so this Newton's third law of motion allows this fish to swim. Here's another example. Birds also depend on Newton's third law of motion. A bird is pushing down on this air, and the air pushes back on the wings and allows the bird to be lifted and fly. Here's another example. So the reaction that takes place within a rocket is an application of Newton's third law of motion. The rocket exerts a force pushing the gases out of the back, and then that is pushed back in an equal and opposite way, propelling our rocket forward. So let's look at some things that are not paired forces. So here are two people, and they're acting or pushing on this same box. Since they are pushing on the same object, this is not an example of paired forces. Even though they're pushing with the same force, these are balanced forces with a net force of 0 newtons, but they are not an example of Newton's third law. But what are some examples of Newton's third law of motion in this example? Well, let's look and think about this real quickly. If this guy right here is pushing on this box with a force, the box is pushing back on him with an equal and opposite force. Here this man is pushing against the ground with his foot, and the ground is pushing back on him. That's allowing him to stay standing. So he's pushing down on the ground, and the ground is pushing back on him. Here's another example that is not a paired force. So this is not applicable to Newton's third law of motion. Here, gravity is pulling him down, and air resistance is pushing him upwards. But both of those forces are acting on this cute little elephant. So it is not paired forces. There are some paired forces here, though. We could say this elephant is pushing on the air, and the air is pushing back on the elephant. That would be an example of a paired force there. So one more thing we need to talk about is momentum. Here is something that's a little confusing. Momentum is noted by the letter P. So if you see an equation and it says P equals, that means momentum equals. So momentum is defined as the product of mass times velocity. So momentum, which is P, equals m times v. And objects that interact through action and reaction forces that we've seen in Newton's third law of motion swap momentum. And objects may act differently, and that depends on their masses and on their velocities. So like I wrote on the previous page, P equals mv. In addition to velocity, momentum also involves mass, and we know mass and inertia are related, so momentum also involves inertia. So what do you guys think this means when we talk about momentum on the road? So what does this mean when we share a road with a semi-truck? Well, let's think about it. If we have an 1,000-kilogram car that's moving at 80 kilometers per hour, my momentum of that car is mv, which is 1,000 kilograms times 80. So that means my momentum is 80,000. And our unit for momentum is kilograms. And then whatever your distance unit is. So this is kilometers. So kilometers per hour. So what does this mean if we are dealing with a large semi-truck? Well, semi-trucks are significantly larger than cars. So let's say that we're dealing with a semi-truck that is 20,000 kilograms. So that's the mass. And, semi-trucks frequently don't go quite as fast. But let's say that for the sake of this argument, this semi-truck is still going the same speed. So 80 kilometers per hour. Then that means the momentum of this semi-truck is 20,000 kilograms times 80 kilometers per hour. And that means that our overall momentum for this object is 160,000 kilometers per hour. So what this means is that when you run into a semi-truck, or if a semi-truck hits you, they hit you with so much more momentum because of their mass. And that's an important thing to realize for the road. There's a great video about momentum in this video section. I'd like you to go watch it, please. This wraps up our understanding and our summary of Newton's laws of motion. Hopefully, you understand Newton's first, second, and third laws and how to apply them.